Hi folks, we're going to take a look at page 99, number 14. So here they tell us that f at x has the form ax squared plus bx plus c, where a can't be equal to 0. So in other words, they're telling us that f is a quadratic function, and they're giving us three pieces of information: that the function value at 0 is 0, that the limit as we approach 1 is equal to 5, and the limit as we approach negative 2 is equal to 8. And they're asking us to find A, B, and C. So not surprisingly, since I need to find three unknowns, I'm given three pieces of information. Okay, so again, this is essentially we're solving a system of equations for A, B, and C. Okay, now this is very clear. F at 0 is equal to 0. Okay, this here, limit as x approaches 1 of f at x being equal to 5. Normally, the only thing we could conclude from this statement here is that the function values approach 5 as x approaches 1 from the left and right. But knowing that this is a quadratic function, which is certainly a very nice function, as all parabolas are, okay, as x approaches 1, or as x approaches any value in the domain, okay, pick any value in the domain, and we see that the function values just approach whatever the value, say I'm approaching x equals a, the function values will always just approach f at a. Okay, so again, normally we can't make that conclusion based on this statement itself. However, knowing that it's a quadratic function whose limit will always just be equal to the function value, we can make the conclusion that not only is f at 0 equal to 0, but f at 1 must be equal to 5, and similarly, the function values here are just going to approach the function value at negative 2, which is 8. And so here we can say f at negative 2 must be equal to 8. So again, I just want to impress upon you here that we can only make these conclusions because we happen to be dealing with a nice function like a quadratic. Okay? But once we have this, we can start now solving for the different values. Now here, something very nice is going to happen is when I take f at 0, okay, the first two terms just disappear. So that's just equal to c. And if I know that f at 0 is equal to 0, right off the bat, there was really no work to be done here. So in the end, we won't have to really solve three equations and three unknowns because we know right away that c is equal to 0. Okay, now let's take f at 1. Okay, so f at 1 gives us a times 1 squared, so a plus b times 1 is just b, and then I'm not going to bother with c because I've already established that that's equal to 0, and so here f at 1 is equal to 5, so a plus b is equal to 5. And then I'll do similarly with f at negative 2. Okay, so here negative 2 squared is just 4, so I have 4a, and then here minus b times negative 2, so minus 2b. And we know that, or we're given that f at negative 2 is 8, so 8 is equal to 4a minus 2b. Okay, so now from here, solve it however you like. Since this is such an easy equation, I guess I'll just solve it by substitution. So 5 minus a, so now I'll take this equation here, 8 equals 4a minus 2 times b, which is 5 minus a, and now we can just solve this out. Okay, so 4a plus 2a, so 6a, and then here we've got minus 2 times 5 is 10, and so 6a is just equal to 18, and so a is equal to 3. Okay, and now we can go back, and b is just equal to 5 minus a, so 5 minus 3 is equal to 2. Okay, so our final answer here is that f at x is equal to 3x squared plus 2x plus 0. So I won't write that out. And if we want to do a quick check here, well, clearly f at 0 is equal to 0. So let's check f at 1. So 3 plus 2 is indeed 5. And then let's check f at negative 2. So negative 2 squared is 4 times 3 is 12. Minus 2 times negative 2, so negative 4, so 12 minus 4 is indeed equal to 8. And so we have our function here. Okay, so again, just a reminder that the only reason why we were able to assume that f at 1 was equal to 5 based on this limit expression is because we knew that we were dealing with a function like a quadratic whose limit is always equal to the function value. Okay, that's it.